All right, let's take a look at this word problem concerning a tank that has water and salt in it. When doing a word problem like this, I encourage you to kind of draw a picture so you can easily visualize what's happening in the problem. So we have a tank. The tank has 50 gallons of water. And it also has a certain amount of salt. And I'll just use that function S of t. So S of t gallons, or sorry, not gallons, pounds of salt. So two things happen. It's got water and it's got salt. Now into the tank is coming 5 gallons of water per minute. Also it has salt coming in. So it has 3 pounds of salt per gallon coming in. So it has 15 pounds of salt is coming in per minute as well. Okay. And it says that the mixture runs out of the tank at the same rate. So that means 5 gallons are running out per minute, so that the tank stays at a constant 50 gallons. 5 gallons are coming in, 5 gallons are coming out every minute. Now it was 3 pounds per gallon, and so I take 5 times 3 makes 15 pounds per minute. Over here we have 50 gallons and S of t pounds of salt. And so the ratio here is going to be S of t divided by 50 pounds per gallon. And so just like here, I took 3 times 5 to get 15 pounds. I would take this fraction and multiply by 5. And so I get S of t divided by 50 times 5 pounds per minute are leaving the tank. So that means that there's 2 contributions to ds dt. Okay, so if 15 pounds per minute are coming in, but this fraction is leaving, so that's minus 1/10 times s. And so this is going to be the governing differential equation for the amount of salt that's in the tank at time t. Also, there's an initial amount. The initial amount is given to be that there's 50 gallons of water, which contains half a pound of salt per gallon. So 50 times 0.5 makes 25 pounds initially. And so there is our initial value problem that we have to solve for this problem. So for mixing problems, I encourage you to think about 2 equations. So water, salt, water, salt, water, salt. And always the concentration of salt per gallon times the rate of water per minute gives us the rate of salt per minute. Okay, now from this point forward, we use standard techniques in order to be able to find the amount of salt in the tank at time t. So first off, let's take the governing differential equation and let's write this as s prime plus 1/10 times s is equal to 15. So this is a linear differential equation, so I use the standard techniques for first order linear differential equations. The integrating function mu of t is equal to e to the integral of 1/10 dt. That's e to the 10 over t. And as always, the plus c is not necessary when figuring out the integrating factor. And therefore, the function in question, s of t, will be equal to the integral of the right-hand side here, 15, times the integrating factor, e to the t over 10 dt, all divided by the integrating factor, e to the 10 over t. Okay, so doing the integral, we get this to be 150 e to the t over 10 plus c, divided by e to the t over 10. So this is 150 plus c times e to the minus t over 10. Okay, the one thing that's missing is the value of the constant c, and for that we will use the initial condition that c of 0 is equal to 25. Sorry, s of 0 is equal to 25. S of 0 is 25. That's also equal to 150 plus c times e to the 0. And so that means that c is equal to negative 125. And so that gives us our solution of this initial value problem is 150 minus 125 e to the negative t over 10. And that is the amount of salt in the tank at time t. Okay, now let's take a look at the other parts of this problem. Determine the long-range behavior of the solution as t goes to infinity. So if we take the limit as t goes to infinity of s of t, okay, clearly the 150 we leave alone. And this part, as t goes to infinity, because I have a negative in the exponent, that part goes to 0. So 125 times 0, which equals 150. Okay, so the last part characterizes the stability of the equilibrium point. The equilibrium point is going to be 150. And just from calculating this limit, that's going to be a stable equilibrium. Now this could have been found out going directly to the governing differential equation without doing the solution. So let me go over that again. ds dt is equal to negative 0.1s plus 15. To find the equilibrium point, we will simply set s equal to 0. So 0 is equal, or ds dt equals 0. So 0 equals negative 0.01s plus 15. So s is equal to 150 is going to be the equilibrium point. So let's draw our chart. 150, negative 0.1s plus 15. So that's an s, not a 5. If I plug in 150, I get 0. If I plug in a number that's bigger than 150, something bigger than 150 times negative 0.1 plus 15 will turn out to be negative. If I plug in something that's smaller than 150, I get something that's positive. And so the derivative is increasing to the left of 150, and it's decreasing to the right of 150. And so from the picture, I can see that this is going to be a stable equilibrium without actually having to do the calculation. Okay? So that is an alternate way of quickly finding the stability, or finding the equilibrium point and assessing its stability without actually having to do a couple of integrals to figure out the answer.